All right, well, now let's talk about the iterator follow paradigm. That's really at the heart of monocurl. So this is a lesson you definitely want to pay attention to. I think after this lesson, a lot of the stuff is just stuff that's good to know. It's good to know, but it's not fundamental. This is definitely fundamental. So let's try to pay special attention to this. All right, so we said that we have let and var variables. I kind of lied. There's actually a third variable. It's called a tree variable. So we already technically saw it, right? We already technically saw it because we needed it for some of the previous lesson, but we didn't explain it. So now let's actually explain it. So what happens when you say tree circ equals something? Let me just fill this in for example. So when you say tree circ equals circle, what happens is that there's under the hood there's going to be two variables. So there's one going to be the iterator, and the iterator whenever you just reference circle or whenever you just reference circ, that's going to be the iterator. So iterator is more or less a normal variable. But under the hood there's a second variable. This is what we call the follower. So we have the iterator and the follower associated with circ, but whenever you say circ, you're probably referring to the iterator. Okay. The follower, so if we can do normal operations on the iterator, what's the point of the follower? Well, the point of the follower is that the follower is on screen. So the follower is the actual thing that we see on screen, and then the iterator is what we have. So this tree is our connection to what we have on screen. The iterator follower is the connection to what we have on screen. So what's going to happen is that we'll make changes to the iterator using normal code, and then we'll, using animations, we'll tell the follower about the changes we made to the iterator. So it follows, quote unquote, the iterator from its previous state. All right, so that might have been a bit confusing, but just as a summary, let's actually just go back to the very original thing, is that, for example, the iterator would originally be over here, and then the iterator would be over here, right? Because maybe we say first the circle is first circ is a circle, and then we would say circ equals a square. All right, so that's kind of what we're doing over here, is that first we have circ equals a circle, and then the next key state is that it's a square. Okay, but now I want to do a continuous interpolation, so the follower would continuously follow from this state to this state. So the iterator lives in discrete time, it goes through the discrete steps, but the follower, it lives more in continuous time, where it might do a continuous step to get from here to here. Again, hopefully with examples it'll become more clear. So let's actually take a look at one. So the simplest follower animation is set. And all set does is whatever the iterator state is, the follower will follow to that state. Oh yeah, another thing to point out is that initially at this point, the follower equals the empty set, right? So the follower, by default, the follower is just completely blank. So this means that even if I have this tree variable and I have a follower, if I don't have any animations, you can't see anything. So we need to actually have an animation to tell the follower about what changes should happen. All right, so wait one, that's just an animation that does nothing. Okay, so before this animation, the iterator is pointing to circle, the follower is pointing to nothing. Now we're going to do a set animation, and remember that the set animation takes the follower and it moves it to the iterator. So at this point, we would have the iterator pointing to the circle, and the follower also pointing to this circle, right? So now at this point, we will be able to see the follower on screen. So let's actually just try that. So we don't see anything for the first second, but after this point, the follower catches up. All right, okay, so we're still in this state, and then we wait for a second, and now I'm going to use functor logic, so I'm going to change the radius of the circle to 2. And at this stage, remember, we just changed the iterator. We just changed the iterator at this stage. So we still have to update the changes to the follower, and I'm going to do that with the set, because again, that's the only one we know. So after this set, then the iterator will be pointing to the circle with the radius equals 2, and the follower will be pointing to radius equals 2. Okay, I do want to emphasize though, is that this circle.radius, that's not making any changes to the follower, it's only making changes to the iterator. So let's copy paste the entire thing. Let's see the output, and then I'll just do a small modification to emphasize the nature. Alright, so hopefully this makes sense. We wait one, then we update the changes so that the follower goes from the empty set to this initial circle. Then we wait for a second, and then we make it so that it grows radius. But note that even if I put the circ.radius over here, even if I put it all the way over here, we would still have the same behavior, because even though it's before the wait, because it might look like I'm doing this before the wait, so we should see that it wouldn't change anything because we're only having the follower follow in this animation. Right, so we get the exact same behavior whether I put the circ.radius before or after the wait, because what matters is actually that the set is happening after the wait. Okay, other things that's pretty cool is that we can use set on scene variables. So the background and camera are what we call scene variables. So I can change the background to blue, for example. It's a special variable. And we can do set on that exact thing. So camera and background, they have iterators and followers of themselves. But more often than not, iterators and followers refer to meshes. Okay, that's cool and all, but we obviously want to have something more complex than instantly transforming. So this is where right, fade, and go come in. Right, fade, and go are useful for showing or hiding in a more continuous fashion. So let's just take an example of right. I think right looks particularly good. And let's probably reset this back to white. All right, that looks great. So the idea with right, fade, and grow is that we have the previous follower state, and then we have the new iterator state that we're telling the follower to follow from. So we have the old follower state, and we have the new state that's gonna come from the iterator. And the idea here is that, well, we can compare the new state with the old state. And for all meshes in the new state that aren't in the old state, I'm gonna do a write operation. But for all meshes that are in the old state but not the new state, I'm gonna do an unwrite operation. All right, that might seem a bit confusing, but 99% of the time you use write or write, it's probably to write the entire mesh or to unwrite the entire mesh. So I do want to emphasize that despite the name write, you can actually unwrite during this. So I can do text equals this, text equals the empty state, and then that's a mistake. We can just write, and then it'll instantly do that. Let's actually just do that on another slide just to emphasize how we can use other slides. All right, so even though it's called write, all write's doing is that it looks for the changes. So if we have inserted meshes, it'll write, but if you have deleted meshes, it'll unwrite, which makes sense over here because I'm basically deleting the entire state, so we should unwrite everything. And also, just because I use write over here doesn't mean I have to use write over here. We can just as easily do a fade, and just as easily do a grow. Yeah, I do think that it could be confusing how we're doing grow, but it's actually shrinking. I just couldn't think of a uniform name for the action of growing and shrinking. Okay, final point I want to make is that even though it's called write, that doesn't mean we have to use it with text, for example. We can use it with anything. Okay, so write, fade, and grow, we can technically do it anywhere. So I can now say, maybe I could say equals square. Oops. And then we can grow this, and how it's going to work is that, well, all of this stuff is getting deleted and all of this stuff is getting inserted, so it's going to just, again, do the delta. Oh no, we can't see that. All right, let's just put that one more time. Yeah, so we saw how it unwrote this and then it grew in this. So technically between intermediate states we can do that, but that's not very a good transition. So transform is when we have intermediate states and we want to transform between them in a more nice fashion. So let's actually look at how it's done. Again, the idea behind it, all of these animations are called follower animations, and at the core of it, they're all just following. They're all just having the iterator go from the old state to the new state. It's just that the path it takes is slightly different in all of these. So let's look at how transform looks like. All right, so I'll kind of skim over the details. I'll just show how it looks. Let's change this to bulk. Okay. We can see how it's that square to circle. It's a very, very continuous transformation, which is really nice. And final thing I want to point out is that we can have multiple trees, and I can do animations on multiple at once, right? So instead of having to do p plus equals set, dots in shape, we can just have it in one. Oh, and also since I didn't emphasize, I probably should have emphasized this before, this p plus equals, it's just saying add this to the global animation playlist. You don't have to worry about it too much, but all this is just saying is, let me add this animation to the global playlist. You can find more details in the main lesson if you're interested. Okay, let's transform. Okay, and then finally, we can, just like how we had custom meshes, we can create custom animations. So over here, we're doing this slow fade where I'm taking in an iterator. So whenever we have this reference symbol, it means that we're taking in an iterator. And then I'm going to create the return animation. So the return animation is going to be in vector. That's all animations are going to be vectors. In fact, animations are animation trees, just like how we had mesh trees. But I think that's probably too complex, so don't worry about it too much. So we're going to add in a wait, and then we're going to add in a fade. And then this allows us to do a slow fade. Okay, so all things considered, this isn't a super useful animation, but it shows that we can make custom animations, and in the future, custom animations will become more important, so that's why I wanted to emphasize it. And we can just add it just like we can for any other mesh fusion. Okay, if you are interested, I have a good write-up on why the monochrome language is designed with delayed execution in mind. I think this is probably a bit more technical than most people need, so I'll omit it from the main video.